Welcome to Ask and Learn.
So now we have a turbine, and this is a nice simple problem compared to the previous few, where that was little bit vague about what they were actually talking about. So this is kind of our standard. This is more of a standard textbook problem. Those previous problems were more real world problems, which are good to also take a look at, where it's not quite clear exactly what's going on. And you're not given all the information, and you got to make some assumptions, and so that's the real world is messy. Um, so let's see here. We have this turbine, and we have combustion gases entering it at 627 degrees Celsius and 1.2 megapascals at a rate of, did I even write that down? I did not write that down when I transferred to the tablet here, and that is 2.5 kilograms per second. We have air. We're going to assume these combustion gases are air, or close to air, approximately. Um, so uh, it's not, well, anyway, we'll assume that the combustion gases are basically air. Um, there's usually probably more carbon dioxide in there, but then would be in air. But we'll take them to be air, and we're going to take an average heat capacity um, for that as it goes through this turbine. So the average temperature is about, because it exits. Okay, yeah, I guess it exits at 527 degrees Celsius and 500 kilopascals, a half a megapascal. And so we'll take an average temperature of 850 Kelvin and get the heat capacity for air at that value, which is 1.11 kilojoules per kilograms Kelvin. Now, we can look at the change in enthalpy as the air flows through here. And we see we have a change in temperature of 100 Kelvin or 100 degrees C. And so we have the heat capacity times the change in temperature is minus 111 kilojoules per Kelvin. The change in entropy, again, we use the ideal gas relationships, and again, this average heat capacity that we found. And that we get as, and since we know the pressure, we use the pressure form here with P here. And so we get 0.1205 kilojoules per kilogram Kelvin. Now, we have heat transfer out of this turbine, and we're told in the problem that we estimate that to be 20 kilowatts. So energy balance says that the workout equals the negative of the mass flow rate times the change in enthalpy from here to here, minus the rate of workout. And we know all of this stuff now, and we wind up with energy coming out is 257.5 kilowatts. Now, they ask us for the reversible, or the reversible power output. So in the reversible case, we have to, let's see, in the reversible case, we have to change the energy, look at the, basically assume that all the entropy, or all the exergy is extracted. And so then we wind up with this formula, again, for the basically exergy conservation and for the reversible case. And we wind up with 367.3 kilowatts is our is the what do you call it? Is the amount of reversible work that we could get out. All right. Okay. So let's see here. We have then I need the exergy destroyed. Well, the exergy destroyed is just what we actually got out, or what we could have gotten out in a reversible way, minus what we actually got out, and that's 109.8 kilowatts. And then the second law of efficiency is just is this divided by this, and that's 70.1%.